I'm a postdoc at the University of Washington in the Department of Astronomy and the eScience Institute. You'll probably hear about the eScience Institute a little more later today. And I'm going to, so my main focus is on a subfield of astronomy. I'm interested in cosmology, and that's the study of the evolution of the universe with all of its different phases. And the reason there is a connection with all of this is the way we do this is we have theories and models which we then confront with data. And the data comes from astronomical surveys, which in some sense is this kind of data is pretty messy. So extracting information from that and actually matching up to all of this takes up quite a bit of work. And the computer language that I've been using almost exclusively for the past few years is Python. So and before I go on, I would like to point out that I'm going to talk about some stuff with the LSST, which is the name of a survey, Large Synoptic Sky Telescope. And this work has been, a lot of the work has been done with the people here listed as part of the LSST group in the University of Washington. And also, a lot of the work actually is done with Kyle Barbary, who's at UC Berkeley. And so what I want to do here is I'll first try to share why I personally find cosmology, and in particular, I'll only talk about supernova cosmology, why I think this is sort of interesting, what the scientific problem is, and then I'll try to describe the kind of data that we are going to get, and we are going to get to study this problem. And that'll help, I hope, in explaining what the issues are that we have to handle. And then I'm going to discuss this Python code, SNCosmo, which we have been using for a while now to work with supernovae. And finally, I'm going to try to come up with this example where we are trying to generate simulation catalogs for LSST. And I'll try to show how some of the work that we've done with SNCosmo can be taken in and used for that. So the first thing that I kind of want to bring to you is that I think that the universe is an excellent laboratory for testing certain kinds of physics. So we usually think of testing physics in laboratories, and you have much better control of data there. But looking at the sky actually gives you certain things that you can't get otherwise. One is you can probe physical effects at very long time scales, and also at very large spatial scales, which is why there are certain kinds of physical effects that you can see very well here. And as an example, sort of saying that this is not just thoughts, there are at least two effects. Historically, this has been very useful, but right now, at least, there are two effects that we see, two discrepancies of observation with theoretical understanding that are usually spoken in terms of dark matter and dark energy that we see from these kinds of observations that you can't see in any terrestrial laboratory. And it is, I believe, because it probes a different length scale and time scale. Okay, so just to say a bit more about that, dark matter is essentially saying that there is observational evidence that the gravity that we see in stellar objects or the universe at large is stronger than it would be if you thought of all the particles that you could see. So there needs to be either more particles or something else. Dark energy is observational evidence for accelerated expansion of the universe at late times, which you wouldn't expect without either a different kind of gravity or another kind of substance that you might not have suspected. So this is kind of an image that has become fairly popular in the last decade when this satellite WMAP was up. And it kind of shows a bit of this. So the way you're supposed to look at this picture is time flows to the right, and what this conical type of object represents is the distance between particles. And the fact that this conical object is growing with time basically means that the distance between particles is increasing with time. And that's what's called the expansion of the universe, right? And so it just shows that kind of schematically, the universe expanded very quickly at first. That's this inflation shows this very important epoch that we can see afterglow pattern called the cosmic microwave background. And then you kind of notice that this is slowing down because particles exerting gravity are pulling things together, right? And structures form, stars form, et cetera, and what you see later on is that this again curves back out. So the expansion is becoming faster. This acceleration is what I just talked about. And in fact, kind of the first major evidence that people began to take seriously came from supernova cosmology for this. And this was discovered in the late 90s. And it was the three people who were strongly involved in this were awarded the Nobel Prize in 2011. So what's happened now is that we understand that there's something going on, but we don't exactly know what that is. And therefore, the way to go forward is to quantify this expansion at late times very precisely, right? So basically, we want to come up with new probes, but we also want to take the probes that we had and do them more precisely so that we can say that the universe is not just accelerating at late times, but exactly how it's accelerating. By the way, please feel free to stop me and ask questions if you want. Okay, so how does this work? How do you know that the universe is expanding by looking at objects? The general answer is that you look at astrophysical systems or things, and you look at things that you think you know something about, you know certain properties, and you can compute the impact of the expansion of the universe on those properties as you would observe them, and do the comparison of those systems. For supernovae, the way this works is you try to estimate their intrinsic brightness, how much energy they were giving out in light, and as the light travels to us, of course, it goes in all directions, so you get a much smaller amount of light energy in any unit area. And this is affected by the expansion because due to the expansion, it takes more time and is even spread out over larger areas. So if you knew what the intrinsic brightness of these supernovae were, and you tried to compare the time at which they were emitting the light and how much brightness you measure, you should be able to say something about the expansion history. That's kind of the notion here. Is that a question? Okay. So the next thing I want to kind of do is talk a little bit about the kind of data that we have. And it's not just the kind of data we have, it's also the kind of data we are going to be getting from experiments like the Large Synoptic Sky Survey. And actually, I'm going to use some of the stuff that has been set up there because I think that will be an easy way of explaining how this works. Okay, so just to give you some feel about this, the Large Synoptic Sky Telescope, it has a really large field of view. It's 9.6 squared degrees. And it's supposed to scan 2,000 square degrees of the southern sky with a very high resolution camera, which is 3,200 megapixels. So it's going to give digital images of the sky, each field of view, for every time it points the telescope at the sky. And it's going to continue doing that in different colors. So this is a YouTube video that LSST has put up, which kind of explains what I'm trying to say. So you have the place where all the light is going to come, and you have these optical objects, which are actually called filters, right? And when that is in place in front of the camera, the only light that's going to come in is of a particular color. And actually, color is kind of a gross way of putting it. It's a sloppy way. I'll give you a slightly better definition immediately. And so these are actually the filters that you were seeing. These different colored filters have the effect of stopping light. So this one is called U, this is G, R, I, Z, Y. And when one of these filters is on, let's say the U filter, the only light that's going to come in is light which has wavelength in between this range. And even in that case, this is the probability of a photon at the top of the atmosphere actually coming into the camera. So since we are going to be taking data with one filter at a time, you're only going to get light from each of these things. And then the telescope is going to scan the sky. This is also a video that's up on YouTube, actually. I'll put the link in later, I forgot. And what this is showing is a very, very fast, accelerated very quickly, showing how the telescope scans the sky. And the colors actually represent the filters that we just saw. So this is Y. And it'll stop scanning in Y, and then it'll scan in another color. And now it's doing G, and so on. Right? So this is how it's going to look at different parts of the sky. And I'm not going to continue with that video. But at the end, this is an experiment. This is a survey that's going to continue for 10 years. And at the end, you'll be able to add up all those images that you had of particular areas of the sky. And this is what you get in different filters. So what this shows is essentially how dim an object you would be able to see because of that co-addition. So more co-addition obviously means you get higher signal to noise, and therefore you can see dimmer objects. And for example, here, what's being shown is 26 plus 1.24, that's 27.34. That's the red part. And something which has a magnitude of 27.24 is going to be detected at something like a 5 sigma level, is what it's saying. And so here, higher numbers means it's dimmer. And so that means you've visited these points many, many, many times more. And so these red points are actually selected points where the survey is supposed to go more times. They are called the deep drilling fields for various scientific criteria. But coming back to transients, like supernovae that we were talking about, what you get are sort of these individual exposures in different bands. This is actually an example from a previous sky survey, Sloan Digital Sky Survey. And you get two pairs of images. One is what's called a template image, maybe by co-addition or something. And one is the search image, which is what you just saw when you scanned that part of the sky. And you have to take a difference of these two and see if some object is there, because that's a transient. So a transient is something that happens at very short time scales, like supernovae, they're on for a few weeks. And so per image, you see what the difference, the new light there is, and how bright that is. That's kind of the thing that's done, and this is a very complicated process, but there are people who are working on those algorithms. But what all of this is going to give us is something like this, which we call light curve, and that is the flux, or the amount of light that you think that object had, how bright that was at the surface of the Earth as a function of time. Okay? So that's what it is like. And so this is a particular supernovae that the Sloan Digital Sky Survey had. And this kind of data is called photometric data. So it's really digital images. But the source really is not that, right? So we've kind of thrown away degrees of freedom. And just as an example, let me show you, this is 2011 FE, which is a really well-observed supernovae. It came on in 2011. That's how the designations work. And it's so well-known, it has its own Wikipedia page. But this is kind of the light curve that it has. Because it was very nearby, it has been observed really frequently. But there people also have spectra. And what you see is what I'm going to describe as a time series of spectra, right? So this thing that you're seeing, this wiggly line, this is the amount of light energy coming in per unit area, per unit time. But that in bins of wavelength, but it actually changes with time. And what I'm actually showing is, of course, interpolated. But the thing to bear in mind is, even though we have this light curve type of data, the underlying object has more degrees of freedom, and they are described by spectral time series. Now, I said that the main thing that you want to do is figure out how bright those objects are, because that's instrumental in finding out how the universe was evolving. And if you look at the data that I kind of showed, this just tells you how bright it was at the Earth, not intrinsically, right? So going from that to intrinsic brightness is sort of a problem that people have dealt with a lot. And you can sort of understand that in order to decouple these, there have to be features that are different. It's not just the brightness. So think of something like a night lamp and a 100-watt bulb, right? If they actually look different in shape here, but if they had features that were different, then you could actually distinguish between what is intrinsically a 100-watt bulb but looks dim because it's far away, and a night lamp which looks bright perhaps because it's nearer to your eyes. Okay? And the way this has been done is by training on a very large number of supernovae light curves and spectra, so that supernovae at similar times have similar brightnesses unless some feature is changing. So this has been done. I'm not going to describe this process today. And it has been done in multiple ways. And the one that I'm sort of going to try to use is the SALT model. And what this does is actually it trains a spectral time series surface, even though most of the data that it is training with is photometric. So there's a lot of regularization that's required to do that, and that's there. Anyway, what I'm trying to, the kind of codes that I'm going to talk about are codes that actually will work on the test data. And so what you'll do is, for each supernova that you get in your sample, you're going to try, so actually there's a step that you need to convince yourself that this is indeed a supernova 1A, and then you're going to try to fit that to this salt model and get a few parameters that the salt model has. So you can think of those parameters as principal components. It's slightly more than principal components because there's a multiplicative factor that's taken out first, but it's something like principal components plus a multiplicative factor that has been modeled. So now I'm going to try and talk about some code. So this is SNCosmo. The main author is Kyle Barbary. He's at Berkeley. And it's actually very easy to install. You can install it using pip or a setup script or Conda. It's almost entirely written in Python, except parts that become a little slow, and therefore Python was used. But mostly, it's well documented. I'll just show you soon. And large parts have been tested with unit tests. Mostly, it tries to use packages that are already in the Python ecosystem. So NumPy, SciPy, AstroPy, and even a few others here and there are often used. And this is kind of the read the docs page. You can look at that. There's documentation, there's a landing page, there's a mailing list if somebody tries this and has trouble. There's even a chat room, and that's the DOI. And so this is meant to be a Python implementation for supernova cosmology related stuff, mostly from the stage that we get light curves and onwards. So I don't think there is a plan that we will put in stuff that goes from the images to those light curves that I said there's a very important step. That will be in a different place, but all other things that we have to do after that, try to put in here. So such software actually already exists. This is not the first time this is there. The one that I've used most in that kind is SNANA. And one major difference is that those software often are executables, and they're designed for a set of tasks. So they're executables, they have arguments. But here there is no major script. It's basically a library of various functions. And these are very useful primitives. It's the kind of primitives that you would think of if you were, for example, thinking, okay, if I had that spectrum and it passed through those filters, what is the amount of light I would get? Those are the kinds of primitives that are there very easily. So it's very easy to reuse that API and perform other tasks tailored to your needs. A bit about the architecture. So this treats the supernova as a source emitting a time series spectrum at its location. And so that's the astrophysical source. And the most basic one is a time series source. You can take that class and define how you want the spectrum to evolve through a series of files where you define times and the spectra at those times, and it'll interpolate. And then there's the stretch source, which is popular in supernova, which is basically you have a source, and think about the light curves we saw, and the light curve widths in time can be changed. And salt to source is basically a source that is respecting the salt model. It uses that. And then what's there is it knows how to evolve the source at some cosmological distance to us. So there's evolution due to the path, And that includes the effect of the cosmological model. And there are effects like dust so when you get light from distant objects, there's dust in the Milky Way that extincts it, and it can take care of that. And there's also potentially dust in the host galaxy of the supernova, and it can also do things like that. So it has ways of handling that. And what it gives you from when you specify what these effects are is a model, which is the observed spectrum on the Earth. So it's going to be a function of time and wavelength and the model parameters of the source or whatever else you had. So this is completely central to the scheme. This is the light curve model that we just talked about. So this is flux. Theta represents parameters. For example, I'll show you an example of the salt model, and theta are parameters that define the salt model. Once you have that, you can take photometric data and fit that, giving you those parameters of the salt model, which should tell you how bright the supernova intrinsically was. You can simulate photometric data. You can plot light curves or data, and you can use this for photometric typing or photometric redshifts. I didn't tell you what photometric typing was, but I kind of once said supernova 1A is sort of important. There are other kinds of supernovae. They are called core collapse supernovae, and they have a different mechanism of explosion. And those supernovae don't work in the same way that I was trying to describe. They won't follow the salt model. And they're easier to identify if you have spectral data, but as I said, we won't. So you can do photometric typing that way. So I'll just show a bit of how things look. This is how photometric data is represented. It's an astropy table. Some columns are essential: the time, modified Julian date, flux error, 0 point, and the 0 point system is essential. You can have other columns. They'll be ignored if it's not necessary. You can plot that as simply as that. Okay, so SN0 was this table, and if you say plot, it'll give you that plot. You can find the model parameters for salt. You can use a maximum likelihood fit, and this uses I min V under the hood. And the way you do that is simple. You instantiate the model saying what the source is. If you know the redshift, in this case I did because it was independently determined. I set that in, and I say fit LC, and it gives me the fit. The line is the model through the points, and you can see that it's reasonably good. You might want to do something like a sampling of the parameters. So you might say that I don't just want the maximum likelihood estimate. I may want to find the posteriors of the model parameters of salt. So these are the model parameters of salt. T0 is the time at which you saw the peak. X0 is an amplitude. X1 is this stretch kind of object, and color is essentially the slope of the spectrum. And it knows the model because you tell it that the model is a salt model, and then you can say, I'm going to do an MCMC, and these are the parameters that I want to fit, V-param names. Model Z is the model that I'm fitting to, and it gives you the fitted model, MCMC model Z, and a result which has a lot of information on that. And this actually uses MC, which is a package by Daniel Foreman Mackey. And then I just plotted it using another package of that guy, Triangle. And you can visualize what these contours look like. You can look at what these things, the light curves look like as you plot it along with the data they were derived from. So I'll come to another thing, which is photometric redshifts. Redshifts are easy to determine from spectra, but when you have photometric data of the kind that we are talking about, they are much harder to determine. And determining photometric redshifts of galaxies is a big project by itself. But as we described, we already have a model for these supernovae. So you might say, okay, why don't I just fit this? And you can do that. And now what you have to add is you have to add in the redshift as another parameter that you're adding. And you have to specify certain bounds. And this was Sloan data, so I knew that spectroscopic Sloan supernovae are all less than redshift of 0.3. They're fairly nearby. And if I do that, I get a result, I can plot it. You can see that the plots looks very similar. And in fact, that's true. I just show, so this array is the set of numbers for those parameters when z was known. And when z is unknown, they're a bit worse, but they're not terribly worse. And the errors are larger. And so that makes sense. So I would say that's okay. But this is actually not so easy. If I were to change this bound, in this case I was lucky, I knew reasonably well what this was. But if I change this bound and make this a much larger thing, then I'm going to have trouble with it. And that's actually one of the complicated situations that we are running into. And it stems from the fact that the template that we started with is finite. You can do simulations, and I'm going to just skip over that because I want to talk a bit about LSST. I don't have much time left. So the LSST software framework is a really big effort. The data is going to come in a few more years, but there's been a lot of effort in developing software that can deal with that data, and not just LSST data. All of this software can be used for astronomical data in general. Right now, this is a recent development. This is very easy to install using Conda. Takes about 15, 20 minutes once you have Anaconda Python, or even Miniconda. And I'm going to talk a bit about the LSST simulation catalog. And this is being built in order to test different analysis methods. So if you have simulations, you can try to come up with the sort of images that we talked about and see if image differencing works and you can get light curves well. It's also important to understand how to optimize the survey strategy if we have these simulations. And we already have catalogs of galaxies and stars, which are all static objects. So one question that we are dealing with here is, how do we implement transients like supernovae? Because you now need fluxes and other observations for every time you observe things, right? You require those values. And because it's now going to be, and since we don't actually know when we'll be observing a particular part of sky, this means we need to do this for many observations. And a requirement that we have is that these catalogs need to be consistent. So if you take a different survey strategy, you should still be able to look at the same set of objects that are there. So the basic method that we'd like to follow is we'll generate supernova observations on the fly, depending on when the telescope is pointing according to the simulation. And we'll use the supernova model like SALT to provide sets as a function of model parameters. And these properties are going to be assigned on the basis of seeds from the galaxy catalog. So that's what's going to anchor things. And this will have this consistency requirement that if we see a supernova today in the catalog in a galaxy and then go back next Wednesday, we will actually see the same supernova 4 days later, right? So that's what we need to be able to do. And we can use some of the work done in SNCosmo. So SN object is kind of a structure that is essentially SNCosmo, but with SNCosmo model that we talked about, but with fixed source, less flexibility, but added attributes for LSST. And then we have a catalog which uses actually the LSST software, which is the instance catalog framework that's already there. And what this does is it prints out catalogs. It prints out catalogs in a particular spatial area at a single exposure time. And the way this is being done is that it gets the information from the static galaxy catalog that's already there. So it reads what galaxy is there, that sets the random seed, that tells you the properties of the supernova. And once you know the properties of the supernova, you know how to get the flux from them in the ways that we talked about. And that's done by SN object. And so this is a way in which we could address this problem. And I'll just put up a summary where I'll note that supernova cosmology with this kind of photometric surveys requires several steps. And a lot of these steps will benefit from good algorithms and code. And we do have ways of doing these things, but they actually all can be improved. And Python has a number of packages now that can be used for these kinds of steps. And of the things that I described, we are currently working on scaling the results for much larger numbers so that we can run those tests. That's all I was going to say, but I'd be happy to take questions.